In this video, we want to be able to say that I can measure and classify angles, and I can identify and use congruent angles and bisectors of angles. Before we actually get into these things, we want to go over a little bit of vocabulary. Some things that we've talked about so far is a line. We've talked about a line segment, and we're going to add another sort of shape along with this. The line goes forever in either direction. It has no beginning, has no end. The line segment has a start and has an end. And a ray is a mix of the two. It has a start, but does not have an end. So a ray could point that direction, or a ray could point the other direction, or any direction. Basically, it's one-dimensional. It has a beginning, and it does not have an end. So let's call this ray over here A, and it's going to go to B. Let's call this other one C, and it's going to go to D. So here's how we talk about it. We are going to say that this one over to the right is going to be ray AB. We can either spell it out as ray AB. We could say AB and put a line over top, but we cannot say ray BA. Order matters. Unlike the line, order did not matter. Ray, we always start with the one at the end point. Always start with the letter at the end point. A is at the end point, so A goes first. With this other ray CD, C is at the end point, so if we are wanting to talk about this, C has to go first, then D, then we put the ray symbol over top of that. Notice the ray symbol is very similar to the line symbol and also the line segment symbol. If we had this being line AB, then we could talk about it being AB with a line over top. Notice arrows both directions saying line. If this was line segment CD, we can say, well, CD with a line segment over top with no arrows, and the ray has one arrow. And it always points that direction, and we always start with the one that is with the endpoint. Opposite rays. Opposite rays form a straight line. Opposite rays form a straight line. So if we have two rays, let's say we have a ray that goes this way, and let's call this ray AB. And let's say we have a ray that goes the other direction. And this ray would be let's go with AC. So in other words, what we have right here, we have ray AC and ray AB are opposite rays. By the way, opposite rays form a straight line, and we are going to get to what the degree of a straight line is in just a moment after we talk about it. An angle. An angle. An angle is made up of two rays, and exactly two rays. And the two rays are actually going to be joined together at a single point. So an angle, we have two rays that are joined together at a single point. And this would be, let's put some letters on this. Let's call this A, B, and C. We can say that this is angle, and we use this symbol right here to say angle A, B, C. Notice the point that goes in the middle is the point that is at the connection of the two rays, at the endpoints of those two rays, the intersecting point. So that's angle ABC. We could also say that this is angle CBA. Order does not matter except for the middle letter. We could also name it this way. Let's say we have, let's put 1 there. We could also say, well, this is angle 1. Let's do another angle. Let's say we have two rays joined together to form this angle. And let's name this can be 2. We can name this as angle 2. We can talk about it in terms of a number, or in terms of 3 letters. Sides. This is in terms of an angle. The sides of the angle are just the 2 rays that are joined together. So looking at this example right here, this purple angle, the sides of this are ray AB and BC. By the way, I messed up whenever I wrote the first ray. Pay attention to the way you write it. Remember, whenever we write a ray, we always start with the endpoint. A is not the endpoint, so we want to make sure that we change that to be BA. Ray BA and ray BC are both sides to angle ABC. The vertex. The vertex is the intersecting point. It's a point that both rays have in common. So vertex of this first one is going to be at point B. The vertex is B. The vertex is a point whenever the 2 angles connect. So we have the vertex, we have the sides, we have the angles, being able to name angles. We're going to talk about what it means to be interior. To be interior, let me draw a plane to be able to describe what an interior means, what interior means. So we're going to have this plane right here, and let's draw an angle inside of it. Okay, we have an angle right here. It's made up of 2 rays. Interior means it's inside. Exterior means that it's outside, as you would expect. And let's go ahead and label some stuff. So let's put the vertex as X. Let's put one of the sides as X going to Y as one of the rays, which is one of the sides, and X going to Z as the other side or other ray. Let's put some points in here. We have point A. Let's put point B. Let's put point C. Let's put point D. Points A and B are interior. They are inside angle YXZ. So interior points, point A and B. We're going to say point A and B so that we know what they are. Exterior points are going to be point C and D. Okay, so interior means it's inside the angle. Exterior means it's outside the angle. Remember, the sides are the rays that are joined together. The vertex is the point at which they are joined together, and the angle. Naming the angle, we use typically 3 letters. We can use a number. And there's special cases whenever we can just use 1 letter, but I'll show you that in a few moments. Let's look at this example. Use a figure to answer the following questions. Part A, name all angles that have B as the vertex. Part B, name the side of angle 5. And part C, write another name for angle 6. So part A, we want to name all the angles that have B as a vertex. So let's go ahead and find B. B is right here. That is a vertex. Notice we have an angle that is right going there with that ray. BC and BA, those are both rays that connect at that angle. We also have another ray with BC, and we have BD. That's another angle that has B as a vertex. We also have BD, ray BD, with ray, we can say BF or BI. That's another angle. And then lastly, we have the ray BF, BI, which also has connection with ray BA. So notice there are 4 angles connected at vertex B. So let's go ahead and name a few. I'm not going to name all of them, like it says. I'm going to name just a few of them. So connected to angle B, we have angle ABC. Notice B is a vertex, so it goes in the middle. We have angle CBD. We have angle DBF. We could also say angle DBI. Then we also have the angle A. Let's write it down. Angle ABF. We could also say angle ABI. Notice we also have those numbers. We could also say angle 3. That's that blue angle there. We could say angle 2. We could say angle 1. I kind of named all the angles, but there's some other variations that we could use as well. So there's a lot of different ways we can name all the angles with vertex B. Part B, name the sides of angle 5. So let's find angle 5. Angle 5 is right here. It's that yellow one that I'm sketching out right now. Okay, so this is angle 5. Okay, well, angle 5 has two sides, right? It has two sides, and the sides are the rays, the two rays that are joined together. So the sides of this is ray FH. Remember, start with the one that is a vertex. F is a vertex of angle 5. And the other side of angle 5 is F to B. Or we can say F to C. Because we get to choose which point. Because that ray extends, we see that we have 2 points on there. Actually, there's an infinite amount, but we only notated that there's 2. So that's naming the sides. Write another name for angle 6. Okay, so angle 6, we are going to look at it in terms of a green angle. I know my drawing is getting messy, but it's okay. We have the idea, so this is going to be this green angle right here. Angle 6 is right, that green angle. Write another name for it. Well, notice we have 3 points on that angle. We have the two sides, the 3 points. The vertex is F, so we need to make sure we have F in the middle. We can either write it as IFH, or we can write it as angle HFI. Remember, order does not matter as long as you have the vertex in the middle. So that's how you will do one like this. Moving on, let's talk a little bit about degree, right angles, acute angles, and obtuse angles. Okay, a degree is a way of measuring. It's a way of measuring our angles. Typically, whenever we are using angles, we use the word measurement. I know yesterday I used the word measurement in the line segments. I should have actually used the word length in those because line segments have length, angles have measure. So degree is a way of measuring an angle. We typically think about it in terms of a complete circle. So a circle has 360 degrees. A line has a degree of 180. So if we went over, this is 180. And a circle, complete circle, has degree of 360. And a degree is just a part of that. Right angle. You guys all have seen right angles before, but I'm going to quickly refresh. A right angle is two rays that are joined together that form a 90-degree angle. And we use that little box there to indicate that it's a 90-degree angle. So right angles is whenever the degree equals to 90 degrees. So let's say that this is, let's just put this as vertex A. I'm not going to put other points on there. We can say that the measure of angle A equals to 90 degrees. By the way, when we're talking about the angles in general, we don't have to put the little m in front. Whenever we're talking about a specific degree, a specific measurement of the angle, we use the m to notate that. Just like with the line segments, whenever we were looking at length, we use, or whenever we were talking about them in general, if we talk about a line segment in general, we put the symbol over top. If we're talking about a line segment length, then we don't put the symbol over top, and we can now say it's equal to something else. So make sure you know when to use the little m and when not to use the little m. So right angle is whenever the measurement of that angle is 90 degrees. Acute angle, it's so cute. It's small. It's petite. It's smaller than 90s. So if we have a 90-degree angle, the right angle is going to be smaller than that. This is an acute angle. So the measure, let's say that this is angle B. The measure of angle B will be less than 90 degrees. Obtuse is big. It's large. So an obtuse angle, we have our 90-degree angle. Just for reference, the obtuse angle is going to be anything larger than that. So the obtuse angle, let's call this C. Angle C, the measure of angle C, will be bigger than 90 degrees. Just really quick to clear up something that I'm sure someone will make a comment about. Notice I'm only using one letter with these. Before I said that we always had to use 3. This is an exception. There's no question about what angle I'm talking about whenever I'm talking about angle C, whenever I'm talking about angle A. And what I'm going to do actually with this, I'm going to make this a dashed line so that we just know that this is just our point of reference. I'm going to make this a dashed line so we know that this is a point of reference. There's no question about whenever I say angle C, that is this angle right here. There's no question whenever I'm talking about angle B that I'm talking about that right there. We're talking about the interiors to it by default. So whenever you use just one letter, typically there's no ambiguity of knowing whether you're talking about that angle or not. Let's look at this example. This is going to be an example in terms of finding a degree. We have ourselves this image. We want to classify each angle as right, acute, or obtuse. Then measure the angle to the nearest degree. Angle ABF. ABF. Well, that's a straight line. That's bigger than 90. So wouldn't that be obtuse? So that would be an obtuse angle. We also want to make sure that we find the measure of that. Straight line, the degree of a straight line is 180. So we are going to say the measure of angle ABF equals 180 degrees. Part B, FBD. F to B to D. So we go F, B, D. That is a right angle right there. We have a right angle. So we have that the measure of angle FBD equals 90 degrees. And we are going to say this is a right angle. And lastly, FBE. So FBE, notice this line, this ray E, is within that 90-degree angle. So it's an acute angle. By the way, reading this would be at 30 degrees. So we are going to go 10, 20, then 30. So we are at 30-degree angle there. So measure of angle FBE equals to 30 degrees. And this is an acute angle. Okay, so just make sure you guys understand that on how to classify. It's not anything too new, anything too challenging. Let's look at some vocabulary. In another video, we talked about the segment addition postulate. We're going to talk about the angle addition postulate with this one. Angle addition postulate is just like the segment addition postulate, but we're talking about angles. So if we had two angles joined together, so we have this angle here, and let's join together another angle. And let's call that this is, let's put some points on this angle. We have A, B, C, and D. Ray BD is interior. So with this one, we can say that the angle, the measure of angle, the two smaller angles add to equal the larger angle. That's the angle addition postulate. Just like the two smaller segments add to equal the larger segment, angle addition postulate, the two smaller angles add to equal the larger angle. So measure of angle A, BD, plus measure of angle D, BC, equals to the measure of angle ABC. The two smaller angles add to equal the larger angle. That's the main idea I want you guys to get from this. Two smaller angles add to equal the larger angle. Angle bisector. The angle bisector is whenever you have just a regular angle. Let's call this angle A, B, C. An angle bisector is whenever it cuts that angle into two equal parts. Remember, segment bisector cuts a segment in half. The angle bisector cuts the angle in half. So where we notate that, we put a little arch there to notate that those are the same. So we can say that the measure of angle, let's put a point on this ray, let's put that as D. The measure of angle ABD will be equal to the measure of angle DBC because they are the same measure. Remember, it cuts it in half, which means that they are congruent, they are equal. In this example, we are given that we want to let ray CA and ray CB be opposite rays. So we want that. Remember that we said a little bit ago that opposite rays, they basically form a straight line, or they do form a straight line. So they just are opposite each other. Where they are the straight line, remember straight line, we have 180 degrees for any straight line. Let's go ahead and put some points on here. We have point C, which is the point that they both have in common. So that goes on those rays. Then we have A and B, right? Point A and B on those rays. So this is our opposite ray. We have A, C, and B. We are told that ray CD bisects an angle, which is ACE. Okay, well, where is ACE? Well, for demonstration purposes, we're going to just put E. Let's put E over here. Let's say E is right here. So ray CE is going to be right there. So we have angle ACE. Remember, we want to draw a picture to be able to illustrate what's going on. It's always nice to be able to visualize because words can be difficult sometimes. So we want to always be able to visualize what's going on. So we are also told that ray CD bisects this angle. Remember, to bisect an angle means to cut it in half, cut the measure in half. The bisector of a line segment cuts the length. The bisector of an angle cuts the measure in half. So we are going to end up cutting this so that it's approximately half. That looks to be about right. So we're going to say that this is congruent with this angle. So these two angles are congruent. Remember, we show congruence with the little arc. Bisecting the angle cuts it in half, which means that they are the same measure. If we know that the measure of angle ACE equals to 2x plus 4, the measure of angle ECD is 20 minus 3x, then let's find the measure of angle ECB. So our end thing that we want to do is we want to find this angle right there. That's our end goal. That is our goal that we are trying to find. But in order to find that, we need to know what angle ACE is. Oh, we also need to label some stuff. So ECD is right here. Let's put D there. Okay. So ACE is this angle right here. Okay, this is the big angle. So that is 2x plus 4. That's the big angle. We're just trying to visualize what's going on. ECD, that angle, is 20x. Sorry, not 20x. 20 minus by 3x. By the way, if ECD is 20 minus 3x, what is ACD? also 20 minus by 3x because they are the same measure. They are the same angle, basically. They are congruent. So this would also be 20 minus by 3x. Remember a little bit ago that I also mentioned the angle addition postulate, which says that if we add the two smaller angles together, we get the larger angle. So adding the two smaller, we get the larger. So in other words, we get 2x plus 4, that's the larger, equals to 20 minus 3x plus 20 minus 3x. But remember, since we have two of them, we can just say 2 times that amount. Okay, well, let's solve this equation. Remember, we want to start by simplifying. So we want to distribute some stuff. So we have 2x plus 4 equals to 40 minus by 6x. Get those x's together, so we are going to end up adding by 6x on both sides. So we have 8x plus 4 on the left-hand side and 40 on the other side. We want to get the constants together, so we minus by 4, minus by 4. So we have 8x equals to 36. And then we divide by 8 on both sides. So we are going to end up with x being not quite a nice number. 36 divided by 8. 8 goes into 36. It goes into it 3 times. So this would be 24 minus by 36 minus by 24. So this is 2. And this would be 1. Actually, it goes into it 4 times. So let's go ahead and just write 4 instead. So remember, we want to put the right numbers. 4. So this would be 32. Changing what we have, this would be a 4 as a remainder. So in other words, this would end up to be 4 and 4/8. 4/8 is half. So in other words, this would be 4.5 if you wanted the decimal. If you wanted the fully simplified fraction, that's 4.5. Okay, well, that's the x value. That is unfortunately not what we're quite looking for. What we are looking for is the value of the angle ECB. But we don't know anything about ECB because they didn't give us any information. But we do know that ACE, the total of ACE is 2x plus 4. So we could find this angle ACE in order to find the other angle. So what we're going to end up doing is we're going to plug in the value of x into the big angle. So we end up with 2 times 4.5 plus 4. That's the big angle, the measure of angle ACE. So measure angle ACE equals to that. I don't know why I did the lowercase, but we will fix that. So that equals to 2 times 4.5 plus 4. Okay, well, 2 times 4.5 is 9. So this is 9 plus 4, which gives us 13. That's small. That's a very small degree. So our picture is not accurate. That's okay. We just needed a visualization. So we can now say that the measure of angle ACE, this measure right here, is 13 degrees. Okay, I said a little bit ago that a line is 180 degrees in total. We have 18 degrees, which is this. Sorry, not 18. 13 degrees, which is ACE. What's left? So we just go 180 minus by 13. Subtract. We end up with a 7. This would be 10. 10 minus by 3 is 7. 7 minus by 1 is 6. So the answer to measure of angle ECB is going to be 167 degrees. And yes, I know that the diagram, our figure that we have created, is not accurate at all. We just need a visual representation of what's going on to help us to be able to solve the problem.